So in this class I am going to discuss WKB approximation. So this is called actually semi-classical approximation also, because I'll tell you after little later why it's called semi-classical approximation. So what type of problem asks in WKB method? So first they will give you Vx, then they will ask the energy value n state, what is the energy for n state. For large values of n, En is the bound state of energy for n state. En should be bound state energy, and Vx is given. They should ask transmission coefficient through potential barrier. So T, they would ask T the value of T. So WKB method is applicable only 1D case. This important, 1D case only this applicable. 1D and slowly varying potential, time independent Schrödinger equation. So it's solved using time independent Schrödinger equation, this whole system, and it's slowly varying potential. It's applicable this. That's why it's called semi-classical. So slowly varying potential is in the semi-classical region, not purely classical and not purely quantum. So its wavelength it's between this what's called matter wave. The wavelength of this matter wave is between the range of quantum part and classical part. So semi-classical region, it's important. This here is applicable classically allowed and forbidden region, but not at the turning point. So I hope you already know classically allowed and forbidden region. This type of point is not applicable. Classically forbidden means what the kinetic energy becomes zero, less than zero. This region is classically forbidden region. So there is some calculation also. We have to calculate this. We have to use the Schrödinger equation for classically allowed and forbidden region. Here in this case I am giving an example of classically allowed region. So for allowed region, if we use the Schrödinger equation and if you solve this, then this type of we get a term, a double dash term there. So a double dash, we consider a double dash equal to 0. We consider in this form a double dash equal to 0, then we get this type of equation. So when we consider a double dash equal to 0, in slowly varying potential we can consider a double dash equal to 0, and this is the condition of WKB approximation actually. This everything is lying here. That's why it's approximation come. This approximation is a double dash equal to 0. We approximate this. It's exactly not exactly 0, but because of this slowly varying potential, we can define this a double dash 0. What is a double dash and how it's come? We have to solve this whole equation, and it needs so much pages, so much 3-4 board I have to written all these things. So I'm not writing that much now. So you have to, just for understanding, I have to tell you that because a double dash equal to 0, we get this, and after applying we get this. This is actually classically allowed region, or this wave function I have mentioned. Similarly, we have to mention classically forbidden region also. So here phi x, this term at the end of this calculation we get phi x equal to 1 by, it's 1 or I probably, I have to check. One by h cross. It's 1 by h cross px dx, and at the end phi x wave function is c1 root over divided by root over px e to the power plus I by h cross integration px dx plus c2 root over px e to the power minus I by h cross px dx. This is the end result. So En is the bound state, and bound state energy eigenvalue are found out by quantization condition. So we can apply quantization condition to find out the energy value in this case. So 1 by h cross x1 x2 px dx equal to n pi minus beta 1 plus beta 2, n plus 1 pi minus beta 1 plus beta 2. This is for n equal to 1 to 3. This is for n equal to 0. It's not that much. I hope you already know. And this we can write this 2m e minus v. I have just putting in the momentum term. We have putting this. I hope you already know about these things. 1 by h cross x1 x2. We can put h cross here also, then only this term will exist here. In Sonisar class they put h cross here in this part, so that's why it's a little different here, but everything is same. Like there are actually 3 cases, different cases Sonisar mentioned for residual. For one side residual, one side is not residual. For both sides not residual. This term he added this 0 and pi by 4 this term, and we get this some result here like 1 by 4 pi 3 by 4 pi, this type of term, but I have not mentioned here all this thing. I have give a general formula for this case. So beta equal here, I hope I already know for this 1 2 3, this 0 1 2 for case. So beta equal to 0 when it's there is a residual. Residual means this type of wall. Here let's suppose this type of wall. Here P potential energy equal to infinity in this case, in this side. Here it's some limiting value is there, probably 0 something can be there, but here at the end there is a certain wall is there, but where potential energy is infinite in this case. This is residual, and non-residual means this like simple harmonic oscillator, this wall is not rigid. At this point potential is like this, not infinite at the certain point, that's why it's called non-residual. So for residual, beta equal to 0 when there is a residual, beta equal to pi by 4 when there is smooth wall, Vx equal to finite. So now some there is we have to know some solving question, what type of question, how to solve this, how to attack this question. So trick will apply for non-residual. If the wall is non-rigid like harmonic oscillator, then trick will be applied. Standard formula non-rigid, standard formula will also apply on the non-rigid case. Then dimensional analysis, dimensional analysis also important in this WKB approximation. When we have to solve the question, then this process is applicable. We have to approach this way also. So dimensional analysis is important. We can apply for all cases. And long method by just solving all this thing, all this going through so much type of stuff. We have to at the end we get this result, and this long method is applicable for all cases. Next, WKB method, a energy value there without solving Schrödinger equation. So in this WKB method we get the energy value without solving without solving Schrödinger equation. Quantization condition solve koribo lagibo. To get this we have to solve the quantization condition, and this is the quantization condition in this case. Next, some trick, this is very important trick. If Vx equal to alpha x to the v for event potential, this should be event potential. En equal to alpha bracket n minus half h cross root over pi by 2 m naught alpha 1 by v plus 3 by 2 factorial and 1 by v plus 1 factorial. Not factorial, it's gamma function. 1 by v plus 3 by 2 gamma function by 1 by v plus 1 gamma function. Whole power 2 v plus 1 v plus 2. I hope you understand this. Important, this equation very important. And n value will be n value will be 1 2 3 4 in this case. If you want n equal to 0, then replace n by n2 n plus 1. If you want to take n 0 from 0, then you have to replace n plus 1 here in this case. Then it becomes n plus half, I think. It's become half. Then dependency of En on n. So what is the dependency of En, energy on n value for large values of n? En proportional to n to v by v plus 2. This is the dependency. The dependency of En on alpha. So En on alpha 2 divided by v plus 2. V plus 2 is common here. Everywhere v plus 2 common. 2v is common. Here 2 only. Here v is not. V is absent here on this case. So you have to remember like this. Next, transmission coefficient. You have to calculate this transmission coefficient also. There is maybe some question may arise from this. So t equal to e to the power minus 2 gamma. So gamma equal to 1 by h cross x1 to x2 twice m vx minus e dx. So this is the actual formula for transmission coefficient. Here vx agote likhi chai. So I have to understand all this thing.